Question 5, Part B. Explain in terms of its structure why graphite can act as a lubricant. So looking up at the structure of graphite, you can see in this structure that graphite is arranged in layers. So layers of hexagonal rings, and we have, so carbon is bonded to 3 other carbons, and we have 1 electron that's unpaired, and that electron holds the layers together. Okay, so it's asking you to describe the bonding in graphite in some ways, but more specifically it's asking you why it can act as a lubricant. So it's asking you to describe the intermolecular forces between those layers. Okay, so we're talking about the intermolecular forces between those layers. Okay, so we need to say what they do, so they can slide or slip past each other. So the layers slide or slip past each other, and now you need to state the reason why, because you have an explain term here as well. So the reason they can slide or slip past each other is because they've got weak intermolecular forces of attraction between the layers. So weak intermolecular forces of attraction between the layers. Okay, so that will give you 2 marks for this question. First mark and second mark here. The structure of graphite has one feature in common with metals. This feature allows graphite to conduct electricity. Suggest what this feature is that will allow graphite to conduct electricity. Now, the thing here is to say about the delocalized electrons. And that will carry a charge or allow current to flow. So delocalized electrons, 1 mark, which move and flow through the structure, 2nd mark. Okay, so the next question is about Buckminster-Fullerenk's, our little buckyball here, carbon 60. So in 1985, a new form of carbon was discovered. It was called Buckminster-Fullerene. After the architect Buckminster Fuller, who designed buildings with complex geometric structures. Buckminster Fullerene's C60 has a simple structure containing 60 carbon atoms per molecule. It looks a bit like a football. Suggests why Buckminster Fullerene's has a lower melting point than diamonds. Okay, so we're looking at carbon 60, so if we're looking at diamond has an infinite number of carbons depending on the size of the structure, and all those carbons are covalently bonded together. If you look at this Buckminster-Fullerene, so you see it's got alternating 5-membered and 6-membered rings, and you can see each one has 3 bonds of any one carbon. So again, these balls can associate with each other, and there's an intermolecular force of attraction between these buckyballs. So it's going to require energy to break that intermolecular force, but that intermolecular force won't be as big as that's required to break diamond. So the answer to the question will be something that will explain that. So part 1 was to state that it is not a giant structure. You could also have said, which would have given you the same marks, that it has smaller molecules, and that's the C60 molecules, so they're smaller than that of the diamond. Okay, the second mark was to say it has weak intermolecular forces of attraction. And the final mark is to link this back to the melting points, and that is to say no covalent bonds are broken when melting. So any 2 from the following 3 points would have given you 2 marks in total.